Hey kids, one of the things that you identified as a challenge for you from when you're solving problems is to be able to recognize what equations you would need in order to solve the problem. A lot of people dismiss the importance of identifying the unknown of a problem, and I really want to focus on how it's going to help you here in solving any of these problems. And then we'll take a look at an example problem that you could give a shot at the end of the video. So this is a typical problem that you may see, that I have two charges, a 15 microcoulomb positive charge that I called charge 1, and a and a negative 6 microcoulomb charge that I called charge 2. And there's a point we called point A off to the right. And I'm asking in this particular problem, what is the net electric field at point A? Well, there's a reason why an entire step in solving a problem, I just have you identify the unknown. And in this problem I said, what is the net electric field in point A? So I'm looking for what is the total electric field. The reason why we have a whole step dedicated to just identify what we're looking for is because it really helps you to establish what equation it is that you need in order to solve the problem. A good step that I do is I take the equation sheet. I can see that I have three equations to choose from. And the first one was K times Q1 all over D squared. The second one that I had was force divided by charge 2. And then the third one was actually hidden in that voltage problem that I showed you. E field and distance. So then what we have to do is the intermediate step in between. That's when we start to take a look at our knowns. The whole idea for our knowns not only is to give us information to put into these equations, but it also kind of tells me which one of these three I should use. So taking a look at the problem above, I have a charge 1. It looks like there's a second charge that's involved there, of course. And then, I didn't mark it in here, but there seems to be some kind of a distance away from that point. So I'll have two different distances. There'll be a distance 1 and a distance 2. So I would have to identify which equations only use Q's and D's that I could use to figure out the electric field. This one you can see involves force, so there's no chance I'm going to be able to do that. And this one has voltage in it, so I wasn't given that. There's no chance I'd be able to use that. However, this one right here, that seems to be my winner. I can see that for every charge, there will produce its own electric field. And so for charge 1 and distance 1, it will produce an electric field, and I could use that equation. And according to that, I would have an electric field going to the right. We'll see that in another video. And then I could use charge 2 and distance 2 in order to solve for an electric field caused by charge 2, and you're going to see that there will be an electric field going to the left, and that's the electric field caused by charge 2. And then I could continue on and solve the problem like vectors. But the whole idea is to take a look at what equations you have available, and then how do you solve them. Taking a look at an example problem, typically provided on tests and quizzes, something that looks like this, and I identify every equation that has the variable that I'm looking for. So you can see I have this first one here. That's just a standard E field equation given a charge and a distance. Here's the definition of an electric field, saying that it's the force per charge. And I even have it hidden in this one over here when it's talking about voltage and distance. So you can see I have those three equations to choose from, and often I write each one of those down in my equation. So taking a look at my equation sheet, the ones that have work in it is just this guy right here. That's the only one that I could see. So I can find that work is equal to the change in electric potential energy. Slide. Going back to my work slide here, I can see that I have two more equations that are involved with electric potential energy. This one that has voltage, and this one that just has charge and distance. So, like this one here, let's give this a shot to try to see how we can solve it. How much work is done when moving from a 10 microcoulomb charge from 9 volts to 6 volts. So take a moment right now to go ahead and identify the equations you would use, the knowns that you would have, and try to choose which equation works best for this problem. So in solving this one, my first step is to identify the unknown. What is it that we're actually looking for? And I could see in this problem, it says how much work is done when moving from 10 microcoulomb charge from 9 to 6. So I'm looking for work, and I need to go to my equations to identify what are all of the equations that have work in it. I can see I need to use the equation work is equal to the change in electric potential energy. But the problem is that my knowns that were given is I was given a charge, and that was a 10 microcoulomb. I was given an initial voltage of 9 volts. I was given a final voltage of 6 volts. And so nowhere in here was I given the electric potential energy. That's where a two-step problem would come in, because I still need to know my change in electric potential energy. So how I would find electric potential energy now becomes my new unknown. And again, I would have to take a look to see what equations are involved with electric potential energy. Moving to this one, I can see that I have electric potential energy was equal to voltage times charge. That was the definition of actually voltage. And then electric potential energy was equal to K times Q1 times Q2 all over the distance. Now the problem with this second equation was that I wasn't given a distance at all, and I was only given charge 2. So I wouldn't be able to answer the question, what is the change in electric potential energy, by looking at this problem. However, looking at this equation, I can see that I was given a voltage. Now the issue is I'm looking for the change in electric potential energy to give me the work. So if my unknown is the change in electric potential energy, I would have to reflect that in the equation. So the change in electric potential energy would actually be equal to the change in voltage times the second charge that's placed in that voltage. So now I can see I have the second charge placed in the voltage, I have the change in that voltage, and I could actually solve for how much work is done.